We were examining the operational amplifier usage examples in practice. That is the fifth one, and this circuit is called buffer circuit. What it does, the output V output is equal Vs. So immediately you are going to say that if this is equal, so you've got to connect a short circuit here, this becomes equal. Why you need all these elements? Let me finish it and then answer to that question, why we need that. Well, definitely we need the definition relation of this ideal operational amplifier. Just remind you, Vp minus Vn is equal almost 0, Ip equal In is equal almost 0. So we know these are the node voltages. Always I am trying to remind you, don't forget it, that is ground. So when I said node voltage, that is this node, and this node voltage difference is the node voltage. Vp is this node voltage. So by definition, Ip is equal to 0. That means that current is 0. If that current is 0, this resistance voltage becomes 0. Why is that? Definition relation, isn't it? Current times resistance gives you the voltage, so that voltage is 0. If that voltage is 0, and Vp minus Vn, so this terminals are short circuited, so that means if this voltage is 0, so this voltage is this point voltage. At the same time, it is this point voltage. Since this is a short circuit, it is also this voltage. So that means V out equal Vs has been proved. So this circuit does this. The next question, what is the difference to make these voltages equal by a short circuit and by this operational amplifier? So if you consider this circuit as a circuit represented by this equivalent circuit, this is going to be the Thevenin equivalent circuit that we're going to see it. That we have seen it already, isn't it? That is the Thevenin equivalent circuit. Represent, let's say, circuit A. This circuit output is connected to a resistor which is called RL. So this current here, let me put it in. Since these are in serially connected, that IL current is equal, if this is Vs over Rs plus RL. So what we have proved after, this is without no amplifier, let's say this is no op-amp. So with op-amp, let me change the color now. With op-amp, so we said Vs equal to V0, that IL current here is going to be this V0 is equal Vs, so Vs equal V0 or V output over RL. That is this I have here. Now let's compare those two now, those two currents. Vs is the same, so the coefficient is this, and the coefficient in here is this. So this is RL plus something, this is only the RL. So this is bigger, then this ratio is smaller. So this current is smaller than this. So that means IL, make it that I have is smaller than this IL, let's say IL prime. So what happened is this: the power consumed by this resistor is going to be less in this and it's going to be higher in here. That means you transferred higher power to RL in this circuit and less in this circuit. Why we need that? Let me draw it a circuit A and circuit B here, connected in cascade, we call it. Cascade connection means the output of this circuit is the input of B. If it is so, then it is called cascade connected. So if you consider those two now, and assume that A represents this circuit, and B as load. If I don't put any operational amplifier in between, that means any buffer in here, then what I am going to transfer here, transfer to this element, is going to be this current, isn't it? Directly connected to load. So if I put it here, an operational amplifier, which is this, let me put it in different color, make it this. If I put that operational amplifier in between here, that means a buffer here, then the energy I transfer, or the power I transfer to the load, is going to be higher. So that means this output of this element is this element or this circuit is going to be my useful usage. So I am transferring the power, the maximum power, to this output by using this buffer. That's why the buffer circuits are important. You cannot do it by a short circuit. If you make a short circuit like this in between, then this current that you transfer to B is going to be less, as we seen here. That's why the buffer circuits are important in practice. That is the end of this video.